Hello, everyone. It is 1 minute till 6 o'clock. I'll probably give everyone like 5 minutes or so to get here, and then we'll get started around 6:05. Hopefully, the sound and the picture are all good. Oh, I don't think I'm screen sharing yet. Let me put that up. There we go. Cool. And Pablo's here. Who else is here? Pablo, does the sound seem all right? Hey, Claudia. And maybe one more person. Who else is here? Cool. Pablo says the sound works. It's good to hear. Maybe a fourth person in and out. Can't tell. They keep joining and then leaving. Hopefully they'll figure it out. Oh, Lorenzo's here. Lorenzo, you remember you only want to have one version of the page open. Otherwise, it's kind of got an echo effect. Hey, Steven. Good to hear, Lorenzo. Anyway, like I was saying, I will give everyone a minute or two to get here, and then I'll start working through. I think I'll do the core standards from test 1. I'll do the core standards from test 2, and then I'll graph one polynomial function and one rational function, and that'll be the core standards for unit 3. And then if you have any other questions about extended stuff, or you need me to go back and look at old stuff, I'd be happy to do that. As always, if you have any questions in the course of my work, please stop me and ask them in the chat. I'd love to respond. looks like we got one more person just joined us. We're 5 minutes in. Let's go ahead and do some math. So I'm looking at test 1 from PreCalculus. So this semester, the first test of the third quarter. This is on Unit 5, which was on functions in general. Kind of properties of functions, transformations of functions, compositions of functions, etc. And the core standards were that you could understand the definition of a function, one input, one output, and then that you understood how to compose functions, and that you understood transformations of functions. So here we go. Unit 5, the first unit of the third quarter, and this is the test. So you're reasonably likely to see similar questions to these same core standards from test 1 on the midterm exam for the third quarter. Some relation A takes inputs of students in first period PreCalculus and outputs their age. A relation S takes inputs of ages and outputs a student in first period PreCalculus. Who is that age? Is A a function? Why or why not? So A takes the inputs of the students and outputs their age. So if the input was, say, Claudia, the output would be 17 or 18. If the input was Lorenzo, the output, again, 16, 17, 18, his age. So every student has exactly one age. So if I input a student, I get exactly one age back. So that means yes, A is a function. It's a little large. Every student has exactly one age. You cannot be two ages at once. Cool. Then relation S takes inputs of ages, like 15 or 18, and outputs a student in first period PreCalculus who is that age. So is S a function? Why or why not? No. S is not a function. For any input, the age, there will be more than one student who is that age. So if I said age 17, there are likely many students in our class who are all 17. So there's more than one output for the same input, not a function. What do you think the domain of S is and why? I accepted various answers as long as they were reasonable. I think actually that the domain of S is between the domain of S is from 16 to 18. No one in first period PreCalc is younger than 16 or older than 18. And of course, the domain is the set of inputs that have real outputs. So if you picked, 13, no one in PreCalc is 13, so it wouldn't have a corresponding output. Therefore, it would not be in the domain. Cool. Any questions on number 1? Rockin'? I think that's pretty straightforward. Hopefully. One input, one output. That's the definition of a function. You need to know it. Let's do number 2. Excuse me. Given that there's a function f of x equal to x squared, and a function g of x equal to x minus 3, and a function h of x equal to x plus 5, sketch a graph of each of the following below. F composed with g of x, g composed with f of x, f composed with h of x, and h composed with f of x. So f composed with g would be what happens when I take g and use it as the input into f. So that would be x minus 3 squared. So g of x goes into f of x, and I get x minus 3 squared. G of f of x would be what happens when I take f and plug it into the g function. So if I take f and plug it into g, I'm going to get x squared minus 3. F of h of x is going to be what happens when I take the h of x function, x plus 5, and plug it into f. So that would be x plus 5 squared. And then h of f of x is what happens when I take f and plug it into h. So that's x squared plus 5. So then this takes x squared and goes right 3. This is x squared and down 3. This is x squared left 5. And this is the graph of x squared up 5. So you can see that x minus 3 is a function that moves other functions either right 3 or down 3. And x plus 5 is a function that moves other functions either left 5 or up 5. Whereas f of x is a parent function, a parabola. Cool. So I'm going to, just because I have like cool technology, I'm going to deploy it to try to show you what's happening here. So I'm going to draw an original parabola. Goes up to 4 and up that way. And it goes -1 squared is 1. -2 squared should be 4. And it goes that way. And then I'm going to pull that out. And so the first one, right 3, would be what happens when I take that function and move it 1 space, 2 spaces, 3 spaces to the right. And then B, g composed with f, or x squared minus 3, is what happens when I take x squared and move it down 3. So, whoopsie. So that's 1 space, 2 spaces, 3 spaces down. Okay? And x squared moved left 5 is what happens when I take that same function that we started with and move it left 5. Once, twice, 3 times, 4 times, 5 left. And then x squared plus 5 is the same function moved up 1, 2, 3, 4, 5. And I'm going to label each. So right 3, this is part A. And then down 3, that's part B. And then left 5, that's part C. And then up 5, that's part D. Cool. Any questions on number 2? Okay. Seeing none. Number 3. So if f of x equals sine of x and g of x equals some number k times x, tell me a transformation that maps f to f composed with g if you have a k value less than 1 and still positive. Explain the effect on the amplitude or period of the sine curve. Sketch a diagram. So f composed with g of x would equal, so I'm taking the g of x function and plugging it into sine. So sine of kx, if k equals 1/2, then I'm talking about sine of 1/2 x. Cool. So that's a function that has a different period, but the same amplitude as the sine curve. And a transformation would be, so if I took f, this graph of sine of x, and mapped it to f composed with g, this I would have to dilate about the y-axis by, well, in this case, it would be 2. So that's 1 over 1/2. So 1 over k. And the period would increase. And sketch a diagram. So here's going to be the original sine of x curve. And here's going to be a curve that's doubled in period. Sine of kx. Okay. Then f to f composed with g of k is greater than 1. So f composed with g of x would equal k sine of x. If k, let's see, a number greater than 1, maybe 2. K equals 2. That would be 2 sine of x, which is a dilation about the x-axis by k. The amplitude oh wait, my bad. all wrong. Sorry. F, we're still doing F composed with G. This is still sine of kx. My bad, my bad. Took me a second to catch it. You guys didn't catch me. Sine of kx. If k equals 2, this is sine of 2x. There we go. I was doing G composed with F. My fault. We're still on F composed with G, F composed with G. Same thing, same thing. But here we had a half, here we have 2. So this is still dilate about the y-axis. And it's still 1 over k. Same thing. Hi, Lindy. And it's still the period that would change. The period would, in this case, decrease. Okay, so x-axis, and here's my original graph of sine of x. And if the period decreased, it would look something like that, and that. Cool. So there in red is sine of x, and in blue of kx. Sweet. And part C, F to G composed with F. So G composed with F of x would equal k sine of x. If k equals 1/2, then that might be 1/2 sine of x. This would be a dilation about the x-axis by whatever k is. And the amplitude would decrease. Okay, we could even say 2k. Because the amplitude would just equal k in that case. So it would be like if we had my original sine function. There it is again. Should be getting used to it. That's sine of x. And then now we stretched it out. That would be, oh, I made k double. Sorry. We compress it 1/2. Compression. That's better. So that's an example of k sine of x. for a value of k less than 1, where it gets decreased. And lastly, the amplitude will increase. So g composed with f of x would equal k sine of x still. If k equals 2, that might be 2 sine of x. And we would dilate about the x-axis by k. And the amplitude would increase. Also 2k. And there's a diagram. I'd still have my original sine function. Sine of x. But now, if we increase the amplitude, increased amplitude, something like that. K sine of x. Cool. There's number 2. Seeing no questions, I'll move on. So that was it for core standards for Unit 5 on functions. Let's check out core standards from Unit 6 on exponentials and logarithms. So here I am. I'm looking at the test 2 in PreCalculus, Unit 6, and I'm going to go over the core standard questions. We had 3 more core standards for Unit 6 on exponentials and logarithms. So the first one was that you would be able to find inverse functions. So the isotope carbon-14 has a half-life of 5,700 years, longest of any carbon isotope, which is why it is used for carbon dating, measuring the amount of remaining carbon in an object to estimate its age. The half-life means that after t years, an object with an initial amount of carbon A0 will have a remaining amount of carbon A of t given by the function A of t equals the initial amount A0 times 1/2 to the t over 5,700. You were first supposed to find the inverse function t of a such that t of a equals a inverse of t. So finding inverse functions. I'm going to first rewrite using an input and an output variable. So I'm going to use B and C as input. B equals A0 times 1/2 to the t over 5,700. And instead of t, I'm going to use my input variable, c. Cool. So now I want to solve this for c. So first divide by A0. So b over A0 equals 1/2 to the c over 5,700. And then looks like I could rewrite it as a logarithm. So that means c over 5,700 equals log base 0.5, which is the same as 1/2, of B over A naught. And then C equals 5,700 times log base 0.5 of B over A naught. Which, when I put it in some form T of A, T of A equals 5,700 log base 0.5 of A over A naught. Okay, so if this is the inverse function, then the inputs have become outputs and the outputs have become inputs. So the inputs originally were time in years, and the outputs were the remaining amount of carbon. So the inputs, so for any remaining amount of carbon A of some initial amount A naught, T of A is the time passed. Cool. How much carbon-14 would be left of a 10-gram sample after 100 years? So here I'm plugging in 10 grams to my function that tells me how old stuff is with certain amounts left. So wait, no, sorry. I'm plugging in 100 years to my original function, which tells me how much carbon will be left after a certain number of years. So A of T equals the initial amount, 14 grams. 14 grams. No, sorry, 10 grams. The initial amount is 10 grams. 10 grams times 1/2 to the time input, 100 years out of 5,700 years. So I'm just going to plug that into a calculator. Any scientific calculator could do this. I don't happen to have a scientific calculator on my iPad, but I want 10 times 1/2 to the 100 over 5,700. So 9.88 grams. Cool. Then it says, how long would it take a sample to decay so that there's just 1 gram left? Well, cool. This is just my inverse function. So I have an inverse function that tells me how much time it would take for a given ratio of carbon to be left. So I'm going to use my inverse function. T of A equals 5,700 log base 0.5 of 1 gram to be left out of 10. So again, back to the calculator. How much would be left? 5,700. And really what I did here was T of 1 gram left. And really what I did here was A of 100 years. 5,700 times log base 0.5 of 1 gram left of a 10 gram sample, which looks like 18,935 years. And the oldest human remains currently known are a jawbone that was found in Morocco. If the jawbone originally contained 4/10 of a gram of carbon-14, and it now contains 2 times 10 to the negative 11th grams, how old is the fossil? So again, I'm looking for time. I'm going to use my inverse function, T of A, and this is T of 2 times 10 to the negative 11th, which equals initial amount, equals 5,700, the half-life, times log base 0.5 of, let's see, it's 2 times 10 to the negative 11th out of initial amount of 0.4. So 5,700 times log base 0.5 of 2 times, let's put it over the 2 times 10 to the negative 11th all over 0.4. So it looks like the oldest human remains are 195,000 years old. And really 50, if I round up. 50 years old. Cool. There's all the core standards from Unit 5 and Unit 6. Unit 5 on functions, Unit 6 on exponentials and logarithms. The last thing I definitely wanted to do was go over the core standards from Unit 7, graphing polynomial and rational functions. Not really any questions so far. Hopefully you guys just all understood this 100% and just don't have a single question. I think it really adds to this when there are questions, but if there aren't any, there aren't any. Oh, I'm not quite done. Sorry. My fault. The last core standard from Unit 6 was sketch a graph of f of x equals 3 plus log base 2 of x plus 5 and its inverse function f inverse. State the asymptotes, domain, and range of both functions. Plot and label at least 3 points on each graph. Cool. So f of x equals 3 plus log base 2 of x plus 5. And the inverse function, well, I'm going to do some side work. If a equals 3 plus log base 2 of b plus 5. I'll need to solve for b. So a minus 3 will equal log base 2 of b plus 5. And that means b plus 5 will equal 2 to the a minus 3 power. And b will equal 2 to the a minus 3 power minus 5. Cool. And that means I've got an inverse function. F, well, let's do the inverse function in red. F inverse of x equals 2 to the x minus 3 minus 5. Cool. Now I'm going to use the inverse function. Let's put this up there out of the way. I'm going to use the inverse function to help me make an XY table. So this is my table for f of x. So x f of x. But I'm going to fill in this table using that function. So I can see that this exponent will equal 0 when x is 3. So I'm going to center these values around 3. Let's do 2 and 1 and 0 and 4 and 5 and 6. So 0 minus 3 is negative 3. 2 to the negative third power is 1/8. 1/8 minus 5 is 4 7/8. The first power, 1 minus 3 is negative 2. 2 to the negative 2 power is 1/4. Minus 5 is 4 3/4. Okay. 2. 2 minus 3 is negative 1. 2 to the negative 1 power is 1/2. Minus 5 is 4 1/2. Okay. 3. 3 minus 3 is 0. 2 to the 0 is 1. 1 minus 5 is negative 4. Oh, these should have all been negative. Sorry. Negative 4. 4 minus 3 is 1. 2 to the 1 power is 2. 2 minus 5 is negative 3. 5. 5 minus 3 is 2. 2 squared is 4. 4 minus 5 is negative 1. 6. 6 minus 3 is 3. 2 to the third power is 8. 8 minus 5 is 3. Cool. So, working with the inverse function, I found the x values that corresponded to the outputs of the original function. So I plugged in all of these outputs, 0, 1, 2, 3, 4, 5, 6, into my inverse, found the inputs of the inverse function, or sorry, the outputs of the inverse function, which were the inputs of the original function. So if negative 3, for example, was plugged into the original, negative 3 plus 5 would be 2. Log base 2 of 2 would be 1. 3 plus 1 would make 4. Yeah. So when you plug in negative 3 to the original function, you would get 4. If you plugged in negative 1 to the original, negative 1 plus 5 would be 4. Log base 2 of 4 is 2. 3 plus 2 is 5. But it was much easier to work with these ones, plug them in here, and get these ones. Okay. So I'm now plotting my original function graph, f of x, and I see negative 4 and 7/8, 0. Negative 4 and 7/8, 0, looks like that. Then negative 4 and 3/4 gives 1. Negative 4 and 3/4, 1. And then negative 4.5, 2. And then negative 4, 3. And then negative 3, 4. And then negative 1, 5. And then 3, 6. So I have a logarithmic curve that looks something like that. Because a logarithm cannot have a negative argument, clearly the domain is the set of values greater than negative 5. You can't get negative 5 because negative 5 plus 5 is 0. The argument of a log cannot be 0. So here's the asymptote at x equals negative 5. Asymptote of f of x equals negative 5. Cool. And now I'm going to do the inverse function in red, and I'm just going to switch all of the inputs and outputs. So if I plugged in 0, I would get negative 4 and 7/8. 0, negative 4 and 7/8. If I plugged in 1, I would get negative 4 and 3/4. If I plugged in 2, I'd get negative 4.5. If I plugged in 3, I'd get negative 4. If I plugged in 4, I'd get negative 3. If I plug in 5, I get negative 1. And if I plug in 6, I'd get 3. So there's the inverse function. Also with a super clear asymptote. Let's see. I didn't get 4. 4 minus 3. 6. 7. 7 minus 3 is, whatchamacallit? 7 minus 3 is 4. 2 to the 4th power is 16. Minus 5 is 11, so it would be just up there. Like that. Okay. Clear asymptote at y equals negative 5. So asymptote of f inverse of x, y equals negative 5. Okay. And let's see, I'm going to plot and label at least 3 values on each graph. So on the graph of the original, I'm plotting negative 4, 3. And I'm plotting negative 3, 4. Negative 3, 4. And I'm plotting, how about 3, 6? That looks nice. And then on the graph here, I'm plotting 3, negative 4. And I'm plotting 4, negative 3. And I'm plotting 6, 3. Great. And I've stated the asymptotes to the domain of range of both functions. Domain of, well, let's see. I'm just going to put for f of x, the domain is the set of values x such that x is greater than negative 5. And the range is all reals. So the set of values y such that y is an element of the real numbers. And of course, in F inverse, those are switched. So for F inverse of X, the domain of an exponential is always real numbers. The set of values X such that X is an element of the reals. And the range of an exponential function is always restricted. The set of values y such that y is greater than -5. Whew. Cool. That was all of the core standards from Unit 5 on functions and Unit 6 on exponential and logarithmic functions. Seeing no questions, let's take a look at polynomials and rationals. So I guess I should first look at some polynomial functions and then some rationals. I just grabbed the rationals from today's assignment, but let me take a look at some polynomials from section 4.1, which you guys all presented on. Okay, I guess they didn't require us to do any factoring here. So fine. Oh, no, the ones at the bottom need to be factored. Let's do one where we have to factor. How about that? This one looks pretty solid. So here's 93. So, no, good question, Lindy. Do you have to write the domain and range that way? Of course not. So obviously the domain and range could have been written equally well. Let me grab this so I can move it down. So there's a little more space. And then I'll erase here. So domain could also be written, or this looks like the set of values from -5 to infinity. Another way of writing the same thing. Or -infinity to infinity. And same deal over here. If I can grab it, I'll move it on down. And then erase. So this could also have been written, or from -infinity to infinity, and that could also be written as -5 to infinity. Thank you, Lindy. Good question. You're always welcome to use either inequality notation or interval notation or set notation. Those are all perfectly good ways to write domain and range. There are going to be specific cases where one notation is going to be slightly easier than another notation. Like in that case, I think probably the set notation is more complicated and the easier way was the interval notation. But on a lot of polynomials, on a lot of rationals, the easier way is the set notation, and the interval notation is more difficult. I generally use the set notation because that's the notation your textbook uses in their like answer key and answer documents. So I want to make sure that you actually understand that notation. But, you know, it's all good. So directions here were, let me pull up the instructions. That would probably be helpful for doing this. So let's picture what were the instructions. So analyze the polynomial by following steps 1 through 8 on page 185. I'm actually looking at page 189 in my textbook. This is in section 4.1, which you guys all presented on. And I'm using the steps 1 through 8 on page 185 for analyzing the graph of the polynomial, which is kind of a culminating idea of a lot of the other things that you all presented on. The 8 steps were actually presented by Shiva and Olivia and Lorenzo. So here, thanks to them, you should know the 8 steps for the analysis of the graph of a polynomial function. So 8 steps, these are the ones they're talking about. Okay, so that's looking good. Great. So step 1, end behavior. So to analyze the end behavior, I want to look. Oh, Paulo's saying I should first factor it. Thank you, Pablo, for a suggestion on the factorization. I agree wholeheartedly. That's totally the factorization. We can actually factor a little further than what you've done, but that's the perfect start. But to analyze the end behavior, I don't actually need to do that. I won't need to do that until I get to step 2 and want the x-intercepts. So for the end behavior, it's actually easier to see the end behavior in this format. So the end behavior is going to be the same as the end behavior of the leading power function. Tom and Ivan presented on power functions and the difference between a power function and a polynomial function. And it was really helpful to have that definition of a power function because every time we look at a polynomial, here's a complex polynomial, the end behavior can just be reduced to the end behavior of this power function. So the end behavior mimics, like a meme, x cubed. So it is odd. And it's going to look like that. That's what x cubed looks like. Ooh, x cubed. Cool. And the end behavior will be explicitly as x goes to negative infinity, y goes to negative infinity with it. And as x goes to positive infinity, y goes to positive infinity with it. Okay. And step 2. Find the x and y intercepts of the graph of the function. So now, thanks to Pablo, I'm definitely going to need to factor, agreed. So 2, find x and y intercepts. So the y-intercept is actually easier to see in this form. When I plug in 0, 0 cubed plus 0 squared minus 12 times 0 is just 0. So the y-intercept is at 0, 0, which, of course, is also going to be an x-intercept. But to see the other x-intercepts, I'm going to want that factorization. So factor. I'm going to start by factoring x cubed plus x squared minus 12x. I'm going to factor out an x, so it becomes x times x squared plus x minus 12. And then that factors even further because x squared plus x minus 12 can factor to x, and then x plus 4x minus 3. So, Pablo, I did the same as you with the x plus 4 and the x minus 3, but then I took your x squared plus 4x term and factored out an x from it. So these are my 3 factors. So that means each one of those factors is going to give me an x-intercept. So the x-intercepts are at 0, 0. That's also an x-intercept. -4, 0, and 3, 0. Okay. Determine the zeros of their function and their multiplicity. Well, it's the same as knowing the x-intercepts. So pretty straightforwardly, I can see that all of these have odd. So I'm on step 3, zeros. No e in zeros. At x equals 0, x equals -4, and x equals 3. All have odd multiplicity. Multiplicity. Graph will cross at each 0. Okay, that was step 3. Step 4. I'm going to skip step 4 because we're working on doing this without graphing utilities. Step 5, we're not going to deal with turning points right now because we're sketching a rough graph. And so let's graph a sketch by hand. So here we go. I'm now skipping all the way to step 5. So I have no idea where the turning points are. That's not important for a rough graph. I know I've got a 0 at -4. So 1, 2, 3, 4. I know I've got a 0 at 3. 1, 2, 3. And at 0. I know that the overall end behavior looks like x cubed, so it's going to be going down towards infinity and then come up and then go up towards infinity. So this graph is going to be coming, and it's got a 0 here at -4, and another one here at 3, and another one here at 0. It's going to be coming up. It's going to cross at each 0. So we got something like this, and something like that, and then something like that. Ta-da! Rough graph. I don't know what the y scale is. In fact, in a rough graph, you often don't even need a y scale. Like, because I don't even know the y-intercept. Why even use a scale on the y-axis at all? Something's happening on the y-axis. I'm really interested in the overall behavior of the graph. It goes down, then comes up, down, up. Overall behavior. Were there any later steps? Find the domain and range. That's easy. Oh, so this was step 6. We don't know the turning points. The turning points are somewhere. Step 6. -4, 3. How do you know the shape of the graph? Well, I knew it had to do this in general because it's a cubic. So it had to be, and it was a positive cubic, so it had to be going down on the left and up on the right. So down on the left, up on the right. It has to cross at -4, it has to cross at 0, and it has to cross at 3. So it has to go cross, be up here, cross, be down here, cross, be up that way. It's the only way. I'm going down that way, up that way, and I cross here, here, and here. And other than that, I don't really know the shape of the graph. Like, I don't know how high it goes here. I don't know how low it goes there. But I didn't even put a y scale because on a rough sketch of the graph, which, let's remind ourselves, is the core standard here, is that you can make a rough sketch based on the structure of the graph by hand in a simple case of a polynomial. And then in a complex case, or if you needed complex information, you could use a graphing calculator. I'm not going to test you that you can plug this into a graphing calculator because if you're using Desmos, that's like really easy. What I am testing you on is that in simple cases, you can make rough sketch based on structure. So I need you to be able to see this structure and make something that looks basically like this. Goes down, comes up, goes down, comes up. Sweet. Claudia's on it. So step 7, domain and range. This is an odd polynomial. We'll always have a domain of all reals and a range of all reals. So the domain is the set of values x such that x is an element of the real numbers. Or, thank you, Lindy, probably the easier way to write it, -infinity to infinity. And then the range is the set of values y such that y is an element of the real numbers. So -infinity to infinity. Of course, either one of those ways of writing it is perfectly fine. Pablo, in the extended standards test, you could use Desmos. On the core standards, you don't get to use Desmos. So when you see this standard, which is sketch a rough graph of a polynomial based on the factors and an understanding of the end behavior by hand in simple cases and using technology for more complicated cases, you'll be seeing it on the core standards test, which means you will not have Desmos, which means you'll be in the case of a simple case by hand. Step 8. Where is the function increasing and where is it decreasing? Well, in order to get that, I need to know the minimum and maximum values to know where it's increasing and decreasing. So now I'll go ahead and check my work in Desmos, and we can find out where the turning points really are. So going into Desmos, this is now something that we would not see on the test because you won't have Desmos. You won't be asked about turning points. You won't be asked about increasing and decreasing. But just for a further understanding, we're graphing x cubed plus x squared minus 12x. You can see I got a pretty good sketch. It looks basically like that, except for it's red. Basically like that. Great. So now I can get a sense of my scale. My scale clearly was that this up here was 20.7, right? Everyone could see that that was 20.7. And that point down here was -12.6, obviously. And this was, what did we say this point was? 1.7, -12.6. Hey, negative, so 1.7, negative 12.6. And that point up there, negative 2.4, 20.7. Great. So now I can say, where is the function increasing and decreasing? Step 8. The graph is increasing on the interval from negative infinity to negative 2.4, and then it's increasing again from 1.7 to infinity. And then the graph is decreasing on the interval from negative 2.4 to 1.7. Beautiful. And again, just to clarify, you will not be asked about turning points or maximums or minimums when you don't have Desmos. That's something you can do by hand with calculus, but without calculus, you should not be estimating maximums or minimums without a graphing calculator. You would just use a graphing calculator if you needed to know maximums and minimums. But you should be able to identify by hand the overall structure and make a rough sketch. You would not be able to do this without Desmos. So this step 8, this would be needs graphing utility, maybe Desmos. So therefore, not on core test. If you were asked about it, it would be on the extended standards portion, not on the core standards portion, where you would have access to Desmos. Cool. Any other questions about graphing polynomial functions? Seeing none, let's take a look at a rational function. Okay. Where's a fun-looking rational? Hopefully one we didn't do in class. I'm kind of liking, let's try 26. Okay, and the instructions here are, again, to use the 8 steps you learned to analyze the graph of a rational function. And again, we're going to do that by hand. So page 204 has those 8 steps that we were using in class today. Wow, you really can't read that very well. Let me get the lights back on. Okay. Eight steps for the analysis of rational functions. Step 1 says factor the numerator and the denominator of r, find the domain of the rational. So step 1, factor. So f of x factored could be written as, looks like x plus 2, x plus 1, all over x minus 1. And then step 2, it is in lowest terms. There's nothing to cancel. Oh, but the domain we can find here in step 1. Domain is the set of values x such that x does not equal 1. Because 1 minus 1 is 0, and you can't divide by 0. 2. It is in lowest terms. Check. Check. Locate the intercepts of the graph. Okay. 3. Intercepts. Well, if I plug in 0, I've got 2 over negative 1, which is negative 2. 0, negative 2. And then if I plug in negative 2, I will get 0. And if I plug in negative 1, I'll get 0. So negative 2, 0, and negative 1, 0. And step 4, no symmetry. I can tell that really quick, like these aren't the same on both sides of the y-axis. I can't have symmetry. Cool. Step 5, locate the vertical asymptotes. Great. So step 5, vertical asymptotes at x equals negative 2 and x equals negative 1. And horizontal or oblique asymptotes. Ooh, this one's going to have an oblique asymptote. Super fun. Okay, again, I told you, like, there won't be polynomial long division on the test. It's not a situation that I'm asking you to be able to do. We didn't have any time to go over with it. But since you awesome people are all watching the video of me doing math with your spare time, you get to watch me do polynomial long division just because it's so much fun. So I am rewriting the graph again from its original form, and I'm going to do that by dividing x minus 1 into x squared plus 3x plus 2. So this needs long division. Whew, such fun. And how do you do long division? Well, x goes into x squared x times. X times x makes x squared. And x times negative 1 makes negative x. Subtract. X squared minus x squared is 0. 3x minus negative x is the same as 3x plus x, which is 4x. X goes into 4x 4 times. Plus 4. 4 times x is 4x. Oh, sorry. Forgot to bring down my 2. Bring down the 2 plus 2. 4 times x is 4x. And 4 times -1 is -4. Subtract. I'm looking at 4x minus 4x is 0. And 2 minus -4 is 6. Okay, so I'm left with a remainder of 6. So we're going to put that in their answer. So x plus 4 plus 6 over x minus 1. So another way of writing x squared plus 3x plus 2 over x minus 1 would be x plus 4 plus 6 over x minus 1. So this has an oblique asymptote. So another way of writing f of x is as x plus 4 plus the rational remainder 6 over x minus 1, which means there's an oblique asymptote at y equals x plus 4. Again, not something you need to be able to do for the test. Never came up. Not a core standard. Extended standard that we just didn't get a chance to cover because we're smushing Unit 3, which totally happens. So f of x equals x plus 4, which means that, for large values of x, like 1,000, 1,000 plus 4 is the basic behavior of the graph. This added 6 thousandths is not very much, not very consequential in the graph of the function. So we are now at step horizontal oblique. F of R intersects those asymptotes. Not happening. So sketch a graph by hand. So there we go. By hand. Looking like that and like that. I can see that we've got -2, 0. So 1, -2. 1, 0, 0, -2. Got some other things happening over here. 3, -4, 3, 4. Gonna be 0, -2, 0, -2. Ba-bang, ba-bang. Okay. So I'm gonna sketch in here my asymptote. Oh, whoop, 1, 2, 3, 4. So this is the graph of x plus 4. And the asymptote part is going to be in red. So this is the oblique asymptote. How much fun is that? And then we've got, let's see, we had zeros at -2, 0 and -1, 0. They both have odd multiplicity, meaning the graph is going to cross at both. And we're going to do the actual graph in purple. So we're going to be coming from below the function. It's going to do something like that. It's going to come up here. It's going to come down there. It's going to come. Oh, that doesn't make sense. How's it going to get down and back up without it? Needs another. Oh, I forgot to put in the other asymptotes. My bad. No wonder it didn't work. Okay. Other asymptotes. So we had a red oblique asymptote, and we're going to get some green vertical asymptotes. Those aren't zeros. Those are asymptotes. Vertical asymptotes at x equals -2 and x equals -1. no, x equals, what are we doing? Way back here we got problems. Vertical asymptotes, there are zeros at -2 and -1. There are vertical asymptotes at only x equals 1. There we go. So there's a vertical asymptote right here. Pablo's asking a good question, like what would we write if something like this came up? I'm just going to tell you nothing like this is going to come up. I will make sure the problem is one that does not require polynomial long division, or that you have a graphing calculator and are just looking at a graphing calculator. Okay, so now this is better. We've got now the graph in purple. So again, we were down here. We came up. We came down. We came down. Graph goes off that way. And then it returns from up here. And then goes that way along that oblique asymptote. So let me get back to the red. And the red. Great. Cool. So checking on Desmos. How did we do? We were looking at the graph of x squared plus 3x plus 2 over x minus 1. Ta-da! Very cool. Just like we had predicted, it was coming down from over here. It went up over the x-axis, back down, and then continues back up here. It came up and then down. Of course, it's in purple. Great. Okay. But that wasn't helpful very much to you because that was beyond the expectations of what's actually on the core standards test. So let me do another one that is like what you'll actually see. So let's do a rational function that's similar to what you might actually get. Maybe like 33 looks like a decent one. Okay, so again, I'm using my 8 steps for rational functions. Step 1. Factor the numerator and the denominator. Find the domain of the rational function. So step 1. Let us factor. X squared minus 4 factors to x plus 2, x minus 2. X squared minus x minus 2 factors to x plus 1, x minus 2. Ooh, how exciting. A whole. Sorry, I'm confused, Pablo, by your question. This is all the material we need to know. So this, when we got here to polynomial long division, I realized that this was a problem that was beyond the scope of what you'd be doing in the core standards. This wasn't something we talked about, polynomial long division. Looking at analyzing a graph like this, you might do with a graphing calculator. but this is more complex than I'm having you do by hand. So here I'm getting to one. Number 33 is a rational function that I am expecting you to be able to sketch a rough graph of by hand. So this is going to be the material you need to know for the core standards. Did I answer your question, Pablo? Hopefully. Yes. Good. Cool. Okay. So step one, write R in factor numerator and denominator. Find the domain. Domain is the set of values x such that x does not equal -1 or 2. Because if x equals -1, -1 plus 1 is 0, can't divide by 0. If x equals 2, 2 minus 2 is 0, can't divide by 0. Cool. Step 2, lowest terms. Aha, this time we can cancel to lowest terms. Cancel, cancel. We're just looking at x plus 2 over x plus 1. That's the graph in lowest terms. Cool. Step 3. Locate the intercepts. So x intercepts at x equals -2. Because -2 plus 2 is 0. Y-intercept at -2, 0. And if I plug in 0, I'm going to get 2. So 0, 2. Step 4, test for symmetry. Ooh, this graph is not symmetric. Step 4, not symmetric. Step 5, vertical asymptotes. So vertical asymptotes are at x equals -1. Step 6, horizontal asymptotes. Well, this is the case where the numerator has a degree same as the denominator. So that's going to be the ratio of the coefficients, which is 1 to 1. So y equals 1. At y equals 1. Lindy just asked a great question. What do the holes look like? As soon as I get to graphing, we're going to show some holes on this problem. So number 7, let's move those other problems out of the way so they're not distracting. We can make our 8 steps a little bigger. Graph. And graph. Okay, so I'm putting in some details. I know that there's, let's get some scaling. 1, 2, 3, 4, 5, -1, -2, -3, -4. 1, 2, 3, 4, 5, -1, -2, -3, -4. Okay. I know that 0, 2 is a point on the graph. I know that -2, 0 is a point on the graph. I know that I've got a vertical asymptote at x equals negative, oh, sorry, x equals -1. What am I doing? X equals -1. Okay. And I have a horizontal asymptote, which is going to be in purple at y equals 1. And there we go. I'm ready to graph. So let's see. This graph is going to be, let's see, is it coming in from above or below? Let's plug in like -3. -3 squared is 9, minus 4 is 5. Down here on the bottom, 9 plus 3 is 12. No, sorry, 9, yeah. -3. So 12, 10. So 5 over 10, 1/2. So we're below graph, approaching. I'm crossing at this x-intercept because it has multiplicity of 1. I'm coming down here. I'm popping back up because I'm changing sign. Come to that y-intercept. I don't go down below. I'm just approaching over here. Okay, now we need to remember our hole. Lindy, remind us about what happens with a hole. The hole is at 2, right? 2 minus 2, x equals 2 is a 0 in the numerator and a 0 in the denominator. There is not a vertical asymptote at x equals 2. It's a hole in the graph. So what's going to happen at this hole? Well, if 2 did go in here, 2 plus 2 would be 4. And 2 plus 1 would be 3. So if you plugged in 2, you would get 4/3, but that's a hole in the graph. So we're going to come in here and say 2, 4/3. The graph doesn't exist at 2, 4/3. This is a lack of a point at 2, 4/3. Not there. The graph is not there. It's ghosting at 2, 4/3. Apart from this hole, the graph is exactly the same as x plus 2 over x plus 1. But at x minus 2 over x minus 2, you can't divide by 0. So if you plug in 2, you get 0 on the top and 0 on the bottom. And 0 divided by 0 is just not defined. And there you are. You have a big old ghosting hole right in the middle of your graph. 2, 4/3 is not really there. So Lindy, that's what a hole looks like on the graph. Cool. Anyone want me to talk about anything else before I go? Those are all the core standards for quarter 3. It does look like a hole. I agree, Lindy. It looks like a hole. Pablo set. You are welcome, sir. Lindy's symmetry is not an extended. There was only extended standard back in the second quarter about trig. So there's not symmetry as an extended standard. So neither core nor extended. You kind of want to know about it. It can help you if you realize there's symmetry. It's nice, but I'm not testing for. I'm not asking you whether you understand symmetry in this semester. Claudia, piecewise functions are an extended standard on this test. No, piecewise is the right answer. Oh, are piecewise functions part of the test? Part of the test or on the test? Yes, so piecewise functions are on the extended standard. Piecewise functions were an extended standard from unit 5, the first unit of the third quarter. They're not on the core standard. Do you want me to talk about a piecewise function? Sure. Lindy says yes. Let's do a piecewise function. I'm going to have to disappear for a second and charge my pencil because it's about to die. But let's do that. So I'm still here on voice, but you can't see my screen. And it'll only take like 15 or 20 seconds, and I'll get set up with a piecewise function. Maybe the one from the test, the Unit 5 test, about Jocelyn and the Nintendo Switch. Anything else I should talk about besides piecewise functions? Piecewise functions is a great thing to ask about. Okay, I'm now powered back up and plugging back in. Should last me to cover piecewise functions. Where's my video? There we go. There we go. Back to screen share, location, movie, share. Ooh, average rate of change could also be on the test. Do you want to talk about average rate of change of a function? Yeah, we could do that. Cool. So here I am on number 4, piecewise function. Jocelyn walks away from home at a rate of 2 meters per second towards her friend Michelle's house. After 30 seconds, she stops for 10 seconds, realizing she forgot her Nintendo Switch at home. Then she runs back home in 20 seconds. Sketch a graph of Jocelyn's distance away from home over time above, and then write a piecewise defined function for your graph. Okay, so Jocelyn walks away from home at a rate of 2 meters per second. So she started at home. She's going 2 meters per second. So in, let's see, 5, 10, 15. So this is 5 seconds. She would have gone 10 meters. In 10 seconds, she would have gone 20 meters. In 20 seconds, she'd go 40 meters. And in 30 seconds, she'd go 60 meters. So that's looking like Jocelyn. Right there. Cool. She stops for 10 seconds, realizing she forgot her Nintendo Switch at home. Oh no. Stop. There's Jocelyn not getting any closer or further away from home for 10 seconds. And then she runs back home in 20 seconds. Back home in a mere 20 seconds. So at 60 seconds or a minute later, she's back home. Cool. So that should be your graph there. Okay, sketch, check. And then write a piecewise defined function for your graph. So I see f of x equals the set of pieces starting with, at the beginning, 2 meters per second. So 2x if 0 is less than or equal to x less than or equal to 30 seconds, the first 30 seconds. And then we were just at 60 exactly if 30 is less than x less than or equal to 40 seconds. And then we were going down. We went 60 meters in 20 seconds. So let's see, it was a rise of negative 60 and a run of 20. So that's 3 meters per second. So negative 3 meters per second times x minus 60. She got home at 60. 60 needs to be a zero of that function. If 40 is less than x, less than equal to 60. So at 40 seconds, 40 minus 60 is negative 20. Negative 20 times negative 3 is 60. That's where she was. And then 60 seconds, she's back at 0. There's a piecewise defined function. Questions about piecewise defined functions? Claudia? Should I do a little with average rate of change? Claudia's all set. Let's do an average rate of change problem with, how about an exponential function? That looks kind of cool. So let's take f of x equals log base. There we go. Let's do this one. This one looks way fun. Cool. So we're going to find the average rate of change on that function. Find the average rate of change from x equals 1 to x equals a. Back to the piecewise function, a couple questions here. So where did I get 2x? Well, here the rise over the run was up 2 over 1. And it's also true from the word problem, 2 meters per second. So I could see it on the graph after I graphed it, rise over run, up 2 over 1. And I could read it in the word problem. The rate at which she's running becomes the slope of the graph. And here, it doesn't actually tell me that she's running home at 3 meters per second, but I can see it down 60 over 20. That's going to be 3 meters per second. Got it. Pablo's got it. Okay. Find the average rate of change. We're doing a new average rate of change problem about this one. So we're going to do a problem where we have to find the average rate of change from x equals 1 to x equals a. So the average rate of change is average rate of change. Whoops, can't spell it. Average rate of change. Rate of change is given by f of from, how about rate of change from A to B is f of B minus f of A all over B minus A. And just for the sake of continuity, let's make that a B. So here, I want the average rate of change from x equals 1 to x equals B. So that means I'm going to do f of B minus f of A equals 1 all over B minus 1, which is going to be 3 plus log base 2 of b plus 5 minus 3 plus log base 2 of 1 plus 5 all over b minus 1, which then becomes 3 plus log base 2 of b plus 5 minus 3 minus log base 2 of 1 plus 5 all over b minus 1, which 3 minus 3 cancels out. And I don't happen to know log base 2 of -6, but it's got to be like 2.2 or something. Oh well, we'll just keep it. It's going to be log base 2 of b plus 5 minus log base 2 of 6 all over b minus 1. Cool. And then if I wanted to deploy this expression that I've now written, I could say, then go back in and add to my instructions, then use your expression to find the change from 1 to about 10. So let's let b equal 10. So I have it. Now, if b equals 10, I'm going to have log base 2 of b plus 5 minus log base 2 of 6 all over b minus 1. If b is 10, then that's log base 2 of 15 minus log base 2 of 6 all over 10 minus 1 is 9, which I could evaluate with any scientific calculator, but I have Desmos. So base 2 of 15 minus 2 of 6 all over 9.14. 0.14. So what I just found was that if you took this function and drew this, need a new color, yellow line. Oh, I could use purple. Purple's better. From 1 to 10, the slope of that line is only 0.14. The slope of that line, m, equals 0.14. M equals 0.14. Sweet. Good question, Claudia. Any other questions? On average rate of change. So not core. Okay. If there are no further questions, I'm going to wish you all a good night and tell you good luck between now and Thursday morning, or sorry, Friday morning. You have a number of opportunities. Come in and seek help. Ask me on anything I did on this review session. If you didn't get to see it live because you weren't one of the 5 or 6 people who did, then hopefully you get a chance to watch it between now and Friday, and you can come in and ask me anything that you didn't get to ask in the live stream. Otherwise, good luck. I'll see you on Friday, and I hope it goes well. And then I hope you have a great spring break afterwards. We made it to the end of third quarter. Good work. Bye, Claudia. Bye, Lindy. See you, Pablo.